Have you ever been interested in being able to solve any integral that has any odd power of sine, such as the funny number 0 to pi over 2 of sine to the 69 of x? Well, now you're going to be able to do it. So I will show you how to find the integral of any even, or rather odd, power of sine. And the way to do it is that we will begin by writing our integral, which will go from 0 to pi over 2. And we will write this oddness to have this in general, right? We are going to solve this in general for any odd power as 2l plus 1, right? So sine is to the 2l plus 1, where l is just some entire number, 0, 1, 2, 3, 4, 5. That way, 2l plus 1 is always odd because 2l is always even, and then you add 1, so you get an odd number. So the way to solve this is to quickly rewrite this as sine of x to the 2l and then times sine of x dx. And now what we will do is use integration by parts, our favorite form of integration in this channel. So u is going to be one of these. Now I will choose this one because it's going to be quite easy to take the derivative of it. Integrating it, not so easy. So u is going to be sine of x to the 2l, and thus taking the derivative is going to be very easy. It's simply 2l, this is the chain rule, sine of x to the 2l minus 1, and now times the derivative of what is inside, which is sine, so the derivative of sine is cosine, so we get cosine of x dx. And we choose v, or rather dv, to be sine of x dx. So that would be sine of x dx. So we integrate sine, we get minus cosine of x. Okay, so now we write the integral. So we get that integral from 0 to pi over 2 of sine of x to the 2l plus 1 dx. This is going to be now the product of these two parts. So we get sine of x to the 2l times minus cosine of x, and I have to evaluate this between 0 and pi over 2. But notice that at pi over 2, sine is going to be 1, but cosine is going to be 0. And at 0, cosine is going to be 1, but sine is going to be 0. So in both ends, this is going to be 0 when I plug in my limits. So that means I am only left with the integral, which will be minus the product of those two. So minus integral from 0 to pi over 2. And I get 2l. I have another minus, so we get plus. And then we have sine of x to the 2l minus 1 times cosine squared of x dx. Now, of course, the 2l, we can just take it out of the integral. So this will be simply 2l. And now I'm just going to shove this together. I don't like this space, but of course it doesn't really matter. Okay, and now we will rewrite, because we know that cosine squared of x plus sine squared of x is equal to 1. So that means that cosine squared of x is equal to 1 minus sine squared of x. Now, why am I doing this? Because I want to rewrite this back into sines, and you will see why in just a moment. So this thing right here is what we will use. So I have that, well, my original integral is equal to 2l times my integral from 0 to pi over 2 times sine of x to the 2l minus 1, and then we multiply by 1 minus sine squared of x dx. So here we just multiply through, so we get integral from 0 to pi over 2 sine of x to the 2l plus 1 dx. This is equal to, so we get 2l. Now all we do is multiply through. So we have integral of 0 to pi over 2 sine of x to the 2l minus 1 dx minus the integral from 0 to pi over 2. And now notice that we have this sine squared there. that will add here, because if you have the same base, the exponents add up. So that's simply sine to the 2l plus 1 of x dx. And now notice that even though I used a bit of a different notation, maybe I'll just stick to the same notation, we have the exact same thing on both sides, at least the same integral. So now we can just add this to the left, so we get this same integral that we already had, so 0 to pi over 2, blah, 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 sine of x, 2l plus 1. We have once because it is here, and then we add 2l from this one, right? So we simply add them together, so 2l. And then we are still left with the 2l from here. So 2l times the integral from 0 to pi over 2 sine of x, and this is to the 2l minus 1 dx. Okay, so here we can of course simply divide by 1 plus 2l, so 2l over 1 plus 2l, and just see what we have right here. Because now this integral and these are correlated. What does this mean? This means that if we started, let's say with, I don't know, L equals 5, then this thing right there is integral of sine to the 7th x. No, not 7, sorry, 11. So that would be 11, sine 11x. And here we would have 2 times L, which would be 10 divided by 11, times sine of, look at this, 2L minus 1, right? So the integral, of course. So this is also integral. And this is to the 9th now. So what we managed to do is that we lowered basically our case. We started at some odd number, and now we found that the integral is the integral of the next odd number that is lower times some constant. So this means in this example of L equals 5, we could write this as 10 over 11, and now we use a formula for this, right? If L is equal to 9, right? So, or rather, sorry, if this is to the 9th power, it means L is equal to 4, which means times 8 divided by 9 times the integral of sine to the 7th dx. Under the same limits, I'm just being lazy here. And then you can do it again, right? You can now, because this means L equals 3. So that would mean 10 over 11 times 8 over 9 times 6 over 7 integral of sine to the 5th. And then you can do it again, right? And again and again. So then you would have 4 over 5 times 2 over 3, and then you're basically done. You have one more. In that case, if L is equal to 0, or rather 1 would have to be the lowest we can go to. We would simply have, if L is equal to 1, actually no, that's the case. So if L is equal to 1, that's the lowest possible number we can go to, I believe. So yeah, now then we would still have to multiply, however, by this lower case. Because if L is equal to 1, that means that we still have the integral of 2L minus 1, which is integral of sine x dx between 0 and pi over 2. So what we get is this bunch of constants times this integral. Now, what is the integral? What is the integral, which I will call I1? Now, why? Because we will be using a very convenient notation. We will call this initial integral of sine x to the L plus 1, we will call it simply I of 2L plus 1. And then the integral where it has power 2L minus 1, we call it I 2L minus 1. So basically the index simply tells you what the power of the sine is. So that's why this is I1, because our sine is to the power 1. Between 0 and pi over 2, this integral is trivial, right? I hope you have seen it many times before. Otherwise, I don't know why you're watching this video. So the integral of sine is minus cosine of x, and we have to evaluate between 0 and pi over 2. At pi over 2, this thing is going to be minus cosine of pi over 2. So we have a minus in front, 0, and then minus cosine at 0, which is 1. So we get minus minus 1, which is 1. So in this case, we simply have I1, no further problem. Okay, so that is what the base case is. So now let's just look at this expression right there. So what about this general expression? Because we saw an example, but what in general? So 2L plus 1, we know this is 2L over 2L plus 1 times I 2L minus 1. So in order for us to come up with this general formula, what we will do is just expand a few times. So let's just go for the next term. So this would be times, now we apply this formula for 2L minus 1. So that means we would be at 2L minus 2 and 2L minus 1 times I 2L minus 3. But then we can do it again, right? 2L minus 3, we can write 2L minus 4, 2L minus 3 times the integral of 2L minus 5. And we can continue on and on and on, all the way until we get to the very first term that, as we saw, the first term is 2 over 3. So the first term is 2 over 3 times the integral I1, which we already know is 1. So no need to worry about it. Okay. So in this case, what do we do? So notice we don't quite have a factorial here, right? We don't have a factorial. We have 2L times 2L minus 2 times 2L minus 4 times blah, 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 etc. But we don't have an actual factorial. And in the denominator, we don't have it either, 2L plus 1, 2L minus 1. So we are missing some terms. So what we will do is going to be the following. Notice that down here, we are missing some terms. So we are going to multiply and divide by the terms that we're missing. That way we are not doing anything illegal and the police will not come for us. So we multiply and divide by the terms that we need. So we multiply and divide by 2L, which is over 2L, which is 1. But now we have 2L plus 1 times 2L times 2L minus 1. And then we do it again here. We multiply by 2L minus 2 divided by 2L minus 2. So now we have 2L, 2L minus 1, 2L minus 2, 2L minus 3. And then we do it again here, every single time. 2L minus 4 divided by 2L minus 4. And we just continue going all the way, all the way, all the way. Okay, until eventually here, for example, we'd have to do times 2 divided by 2. And what we get by doing that is that in the denominator, we get simply, I don't know why I made it so large, 2L plus 1 factorial. Right? We can see that immediately, 2L plus 1, 2L, 2L minus 1, 2L minus 2, 2L minus 3, 2L minus 4, and so on and so forth. It goes all the way until 2, and you can just write 1 over 1, which is of course 1. So we have the factorial. But what happens there? Well, in the denominator, or the numerator, sorry, we have every single thing squared. We have 2L, 2L, 2L minus 2, 2L minus 2. But notice that if we factor out a 2 from each sequence, the red sequence and the green sequence, so we factor out a 2 from here, a 2 from here, a 2 from here, a 2 from here, we would get L amount of 2s, right? 1, 2 here, 1, 2 here, 1, 2, and so on. And if we have L terms, we get L 2s. So we have 2 to the L, all right? But then we have the green sequence as well. So there we also factor out this 2L. So we have another 2 to the L. And when we do that, we are left with L times L, which are the first 2. Maybe I'll keep to the color code, L times L. Then we have 2L minus 1, right? Or rather, sorry, we factor out a 2 from all of this, so it's not 2L minus 1, it is simply L minus 1, right? So it is L minus 1, and then we have another L minus 1, and then we have this 2L minus 4, we factor out 2, so it is L minus 2, that's supposed to be red, I guess. I mean, it doesn't matter, but L minus 2, and then we have another L minus 2. And then we just continue all the way to the lowest number. So what this means is we have in red, we have L factorial, L minus 1, L minus 2, and so on. And in green, we have L factorial as well. So what this means is we have L factorial squared. So first of all, this thing is 2 to the 2L. And also we have L factorial squared. So this is 2L plus 1 factorial. And here you can just take this square, factor it out. So you get 2 to the L factorial squared divided by 2L plus 1 factorial. And this, my friends, is the formula. So if you have integral from 0 to pi over 2 of sine of x to any odd power, then this is the formula that gives you the result. All you need to do is plug in L. For example, what if we want to do the integral of a funny number, right? What if we want to do integral 0 to pi over 2 of sine of x to the 69? Haha, very funny number. So we just need to plug it in. 2 to the 69 times 69 factorial squared divided by 69 times 2 plus 1 factorial. And this number, well, yeah, I don't know what the number is. I'm not going to calculate right now, but you could do it. You could do it, and you could have a very fun integral. So yeah, I hope that this was useful to you. And well, if you wanted to have a different, for example, if you wanted to integrate from 0 to pi, you could also do this, right? Integrate from 0 to pi, then you could do exactly the same procedure that we just did. But the important thing for this to work is that you need the boundary terms from this integral, right? When you multiply these two parts together, sorry, I included something that I shouldn't have. So when you multiply these two parts together, you need them to be 0 at the boundary. So for example, integral from 0 to pi also works because sine is 0 at 0 and pi. So that still works. And in that case, the only difference is that the base case here would be integral from 0 to pi. You evaluate between 0 and pi. And here, this thing would not be 0, rather it would be minus 1. So the entirety of this base case would be 2 and not 1. So at the end of the result, you would have to multiply this thing by 2. So that's the main difference. You could also solve that fun integral if you want to do it. So there you go. I hope that this video was useful to you. If it was, please make sure to leave a like on the video, comment and subscribe, and maybe even consider checking out my Patreon. So I'll see you in another video. Thank you very much for watching.